A revolutionary floating bridge in Washington sinks to the bottom of a lake.
Nobody knew if it was going to survive.
A beachfront high-rise in Texas that has to be destroyed.
Mistakes were made. This building was not safe.
An engineering disaster in the Gulf of Mexico causes a global crisis.
Oil was spewing all over the deck. There were a series of massive explosions.
And a collapsing dam unleashes a toxic tragedy.
Se retiraron 7 millones de metros cúbicos de tierra contaminada.
With big builds, even the smallest mistake can be a huge disaster. From miscalculations to misunderstandings. Some with deadly consequences. These catastrophes are every engineer's worst nightmare. With big builds, engineers often push the envelope when testing new methods. But sometimes that can lead to disaster. Like this catastrophe in Washington state that destroyed a vital transportation link, cutting off hundreds of thousands of daily commuters.
Unfortunately, this was a disaster just waiting to happen.
An unexpected Thanksgiving storm that ruined the holidays for tens of thousands.
An old supervisor gave me a call, and he said, "Bridge is sinking."
And fundamental flaws that brought down a 2,000-meter bridge.
It was a race against time, and time won.
Seattle is one of the fastest growing and most innovative cities in the US. Founded in 1851, over the last century, it has prospered around the banks of the majestic Lake Washington.
Seattle is the home of grunge, coffee, and some serious tech giants.
Hundreds of thousands of commuters cross the lake every day, and its bridges are their main thoroughfare. But building a bridge across this vast expanse of water isn't straightforward. As Seattle reporter Jim Foreman explains.
Seattle is a water city. Water is our lifeline, from the fishing to coming out for an evening cruise on one of the lakes. But the problem is you have to get across the lake in order to connect the communities. Big challenge for the designers of these bridges was just how deep this lake is. There was no way traditional engineering was going to work. So they had to come up with an ingenious plan: floating bridges.
This wasn't just an ingenious plan. It was the only plan, as structural engineer Patrick Clark explains.
Lake Washington is very deep. The solid bottom of the lake that was carved out by glaciers is 400 feet deep, and then it filled in with volcanic ash. So you have 200 feet of very soft material, which is not very good bridge foundation material.
Lake Washington is simply too deep and the lakebed too soft to build a conventional bridge. So, in 1940, after 18 months of construction, Lake Washington became home to the largest floating structure in the world, called the Lacy V Morrow.
The bridge was named Lacy V Morrow after a highly decorated World War II bomber pilot who went on to become the director of the Washington State Highway Department.
And he drew upon his military experience when it came to this new project. The 2-kilometer bridge is made up of 22 hollow concrete boxes called pontoons, each about 90 meters in length. The pontoons are bolted together and then tethered with heavy cables to giant concrete anchors that sit on the bottom of the lake and help stabilize the bridge.
Pontoon bridges have long been used by the military and played a vital role in the Second World War. If they can carry tanks, then in theory, they should be able to easily carry a Chevy or a Cadillac.
The mind really takes time to wrap around the fact that you're not driving on a bridge, you're basically driving on a boat floating in the middle of the lake.
At the time, it was a true engineering marvel. But when another floating bridge in Washington, built during the same era as the Lacy V Morrow, failed spectacularly, concerns arose about the safety of the 1940s construction method.
In 1979, a very large storm sank the Hood Canal Bridge. And everybody started questioning our floating bridges and how viable the technology was.
Even so, the Lacy V Morrow Bridge design was so effective across Lake Washington that in 1989 a parallel bridge, the Homer M. Hadley, was opened alongside to increase capacity. Lessons were learned from the Hood Canal Bridge disaster that guided engineers when building the Hadley. But unfortunately for the Morrow, 50 years of heavy traffic had taken its toll.
Engineers analyzed the Lacy V Morrow and decided it needed reinforcing. While they were at it, they planned to widen and resurface the road to meet new highway regulations.
The idea was to blast away the existing deck and then cut holes on the north side of the pontoons, which would be sealed with watertight hatches to allow for future access and maintenance of the pontoons. The bridge was closed and renovation work began on June the 23rd, 1989. In November 1990, on Thanksgiving weekend, the bridge was still under construction when a heavy storm began making its way towards Seattle.
In the middle of Thanksgiving week, it started to rain. And it rained, and it rained, and it rained. The rain just didn't stop. It was like a fire hose coming off the Pacific. Not only did the rain keep coming, we had the wind.
Strong wind and rain began battering the bridge. On Sunday, November the 25th, reports were coming in that the Lacy V Morrow Bridge was in trouble. Structural engineer Patrick Clark was alerted as the disaster was unfolding.
I was at home. An old supervisor of mine gave me a call real early in the morning, and he said, "The Lacy V Morrow Bridge is sinking, and I need you up there immediately."
Seattle reporter Jim Foreman rushed to the scene.
I jumped in my car and finally got here, made our way to the edge of the bridge. What I could see was these giant concrete pontoons bending and twisting. It was something I've never seen before.
The center pontoon began to sink, pulling some of the others down with it.
Hour after hour, more and more the bridge was falling apart and finally doing the death roll as they go down to the bottom.
By the end of the day, after half a century of safely carrying commuters, Lake Washington's original floating bridge, the Lacy V Morrow, sank. But the danger wasn't over yet.
We were already seeing the one bridge go down, but the bridge right next to it, the new bridge carrying all the traffic, that was in danger too. 110,000 cars used the bridge every day.
The sinking left a massive part of the Lacy Bridge at the bottom of Lake Washington. That was bad enough, but as it went down, it seriously damaged the new bridge next to it, which was already carrying traffic for both roadways.
Because of the close proximity of the two bridges, the support cables holding the adjacent bridge in place were sustaining heavy damage from the sinking pontoons on the Lacy V Morrow.
As the old pontoons were sinking, they were slicing the cables holding the new bridge in place. It was shut down to traffic, and nobody knew if it was going to survive. So engineers came up with a quick solution to save the new bridge. They brought in tugboats. Those tugboats were hooked up to the new bridge and were able to keep it steady against the howling winds.
With one floating bridge being held in place with tugboats and the other one at the bottom of the lake, Seattle had lost its lifeline across Lake Washington, and its residents wanted answers.
So they wanted to know why it went down, and they were demanding those answers fast.
With one of the largest floating structures in the world at the bottom of Lake Washington, an investigation discovered that it wasn't just the storm that had caused the titanic destruction of the Lacy V Morrow Bridge. It turns out that the problems could be traced back to the ongoing renovation work designed to safeguard the bridge's future.
During the remodel, they were actually using something called hydroblasting. They were using water to break apart the old deck, and they were going to replace it with new concrete.
Hydrodemolition or hydroblasting uses high-pressure water jets to controllably demolish or clear concrete from a structure.
One problem with hydrodemolition is all that water has to go somewhere. But because the water was blasting concrete from beneath a grungy old road bridge, there were serious worries about contamination. So under environmental law, it wasn't allowed back into the lake.
Instead, engineers decided to store the water inside the bridge, adding considerable weight that had never been calculated for in the original plans.
The pontoons were designed with a safety margin, but pour in tons of heavy water, and it's clearly going to have an impact. Throw in a massive storm, and it's a recipe for disaster.
But it wasn't just the hydroblasting that had left the pontoons increasingly vulnerable in a heavy storm. It turns out there was another fundamental factor in the renovation work. The watertight hatches were never installed, as consultant Donald Dusenberry explains.
During construction, there was a time when these holes were cut, the frames were not yet in place. And in that instance, the contractor put sheets of plywood over the lower portions of the openings. So basically, we had openings that were about 10 inches above the water, covered with plywood to prevent wave splash and water from getting in.
As the storm raged on, the open holes that were intended to hold the watertight hatches were allowing water in instead of keeping it out.
No one knew that a massive Pacific storm was coming in. They hadn't planned for that, and so the water kept coming in. This was a real catastrophe.
In the end, the weight of the water from the hydroblasting and the heavy storm was more than the bridge could take. The upgrade was meant to save a 50-year-old bridge, but instead, it was an engineering blunder that caused its demise.
This is one of those disasters which seems obvious in hindsight, but at the time, the engineers believed that the pontoons had capacity to spare. But in the end, it just wasn't the case.
In September 1993, the new Lacy V Morrow Bridge opened, replacing the original floating freeway. For 3 nights, crews drove 8 flatbed trucks loaded with concrete slabs across the new floating bridge to prove that this time it could hold its head above water.
Luckily, the bridge was closed for construction, or this disaster could have been a whole lot worse.
When tasked with building big, engineers must start from the ground up. Getting the foundations wrong will almost always mean a structure is doomed to fail. Like this miscalculation in Texas with a beachfront tower that just couldn't stand up.
Padre Island is just sand.
We had a structure with a failing foundation.
A condo building reduced to thousands of tons of rubble.
This tower broke records for all the wrong reasons.
In southern Texas, on the Gulf Coast just north of the Rio Grande, sits South Padre Island, boasting some of the longest beaches in the United States.
South Padre is what's known as a barrier island, a long, thin, sandy strip separated from the mainland by water. In this case, by the narrow, shallow Laguna Madre. It's basically a gigantic sand dune, stretching 130 miles, or about 200 kilometers, along the Texas coast.
These seemingly endless beaches have long been a draw for tourists. In 2006, to accommodate more visitors, construction began on a new 135-meter beachfront high-rise, aptly named Ocean Tower.
The plan was to build a 31-story tower with 134 luxury apartments with marble floors, jacuzzis, and amazing views over the Gulf of Mexico. It would be the pride of South Padre and the tallest tower for miles around.
Yet there's a reason tall towers are rare around here. South Padre sits right in the path of hurricanes. So engineers had their work cut out. Foundation engineer B.J. Ariel knows this part of the Gulf Coast well.
So in the Gulf Coast, we see that there are more of 10 to 15-story buildings rather than very tall, high towers. If we look at this resort here, that's probably about 15 stories high, and look at how spread out it is.
Historically, most development on the island was relatively low-lying. Building tall comes with massive technical challenges, and it costs a fortune. Throw in the threat of hurricanes, this sounds like an engineering nightmare.
The plan was that Ocean Tower would consist of two connected yet very different structures. A main 31-story tower, heavily reinforced with 3 concrete cores. Directly attached around the base would be a much lower, wider parking garage. The big challenge here for engineers, the foundations.
The Gulf Coast of Texas is mostly sand and gravel, dumped there over thousands of years by rivers. The ocean then molds the coast, constantly moving and shaping the relatively loose ground. It's a very dynamic landscape.
Geologist Tim Dukes knows what it takes to build on this coastline.
Anywhere in the Gulf Coast is similar to what we have here, with relatively young, soft, unconsolidated materials, and they're relatively wet. So they're easy to erode, and they don't have a lot of strength to support buildings. Foundation is essential to any building, and in a soft environment, one that is easily maneuverable by natural forces, it can be a problem. Padre Island is an island that is actively evolving. The shoreline is not stable just about anywhere in the world. And in an environment like that, where you have a barrier island, it's just sand with a little bit of lagoonal mud in some areas and no firm rocks to support buildings.
When it is spread out, the foundation is also spread out, and there is less likely of differential settlements. That's why in the Gulf Coast, we see more of this kind of buildings rather than high towers, which has more concentrated load, and the foundation is very small.
When you build anywhere, solid foundations are crucial. But on a shifting, sandy island surrounded by water, in the path of high winds, even hurricanes, you have to get it right.
Although this build would be tricky, the engineers were confident that they could overcome challenges of the unstable terrain and hurricane-prone area. Engineering professor John Brigham explains.
So sand, you really might not think you can build too much on this besides a sand castle, but you can, as long as you have the right engineering solution. As long as we can find a way so that our loads from our building can be distributed sufficiently into the soil, we'll be okay. One good option oftentimes is just to go deep, right? If we're gonna drill in here a pile foundation into our sand, if I go deep enough into this system, I can distribute that load both vertically, and if I go even further, I might be able to hit something solid that also provides us additional support.
For the foundations of the tower, engineers chose friction piles. Long steel rods driven into the ground, deep enough that the friction from the surrounding material secures them in place.
One potential solution for building on something like sand is to use a pile foundation. Now, those are going to be long, thin structures like this that are going to support our building, and the thought is that the deeper into the ground we go, the more strength we're going to provide. Now, just like this umbrella, right, if I just stick it into the ground, it's not doing much for me. It's pretty easy to move up and down, and it's pretty easy to move side to side. But as I drive it in, it's both going to become more stable from wiggling, but also harder to move up and down, giving us that vertical strength. Even though as I'm going down, the sand itself is not necessarily providing a lot more strength. It's about the sand all along the sides that's providing that frictional resistance as I'm driving this into the ground.
The friction pile method is well established. But during construction, it became clear that something was seriously wrong. And in November 2008, developers realized that South Padre Island's groundbreaking ocean tower was suffering from major structural issues.
Before construction was even complete, the tower had started to sink.
A small drop is expected and planned for, but that wasn't what was worrying people.
Nearly all buildings settle. It's no problem if the structures go straight down. But here's the rub. The ocean tower started to tilt.
Although engineers had anticipated the settling, no one had foreseen that Ocean Tower would lean. An investigation revealed that the problem lay in connecting the tower and the garage.
One of the key problems with South Padre Island was you had these two buildings that were connected to each other, and they were quite different, so they settled at different rates. You have one building that's quite tall and thin, being spread over a small area, and another building that's quite short and fat, so it's being spread over a much bigger area. So as they're pressing down, this thin building, this tall one, is getting dropped down quite fast, whereas the short one isn't. And because they're connected, they ultimately tilt instead of just dropping straight down separately.
If you stand on sand with a regular shoe, for example, you'll barely sink. But if you put the same weight on a stiletto, the heel will go straight in. In this case, the parking garage was the shoe, and the tower was the stiletto. They were always going to sink at different speeds. In fact, the tower settled twice as fast as the garage and didn't just sink into the ground, it damaged the foundation columns.
In September 2009, instead of attempting to save the building, the decision was made to demolish Ocean Tower. But it wouldn't be easy.
Even demolishing it was no simple task because you have a very large structure with a very stiff core. This is designed to be able to take high winds. It's designed to be able to stand under an extreme environment. So taking it down in and of itself is not going to be easy.
Engineers faced an unprecedented demolition nightmare. How to bring down 50,000 tons of concrete and steel without damaging the neighboring properties.
One option for taking down a building like this is to use a high reach, essentially a demolition crane to chew the building down.
On South Padre, strong winds were a constant threat, so that ruled out the high reach. It was just too dangerous. Instead, they went for explosive demolition.
The biggest challenge was preventing the tower's 3 hurricane-resistant concrete cores from toppling sideways. To ensure they crumbled safely, the tower was strategically rigged with more than a ton of explosives, positioned at key locations on 8 floors between the 1st and the 26th.
The key to successful explosive demolition is bringing the building down on itself. So you use a sequence of charges to remove key supports and basically collapse it like a layer of pancakes.
On Sunday, the 13th of December 2009, crowds gathered to watch the spectacle. And at 9 a.m., the explosives were detonated. Thankfully, the demolition was flawless, with no damage to surrounding properties, setting a record in the process.
At the time, this was the tallest reinforced concrete structure ever demolished with explosives.
I think you have to conclude with this that mistakes were made, that this building was not going to be safe, and the right decision was to take it down.
With massive engineering projects, safety must be a primary goal in order to prevent disaster. If the measures put in place fail, the scale of the catastrophe can be massive. Like this devastating incident in the Gulf of Mexico that caused a global crisis.
A catalog of failures led to a truly huge disaster.
An oil drilling catastrophe that shocked the world.
Deepwater Horizon was a wake-up call for an industry.
Across the world, global economies have an insatiable need for oil.
Oil and its derivatives are in plastics, fertilizers, lubricants, credit cards, phones, even toothpaste and contact lenses. Our thirst is huge. We get through around 100 million barrels every day.
We have been taking oil from underground for centuries, but over time it has become harder and harder to find, and extracting it safely is no easy task.
The deeper the oil and gas are found, the higher the pressure in the reservoir. Drilling into them isn't like tapping a water well. This is breaking into a massive pressurized cocktail of explosive gases and flammable liquids.
Innovative engineers push the boundaries with new techniques and technologies in order to safely obtain the precious black gold. Bryce Merrill has worked as a rig diver on deep-sea drilling rigs like this one.
What you see behind me is the Mr. Charlie offshore drilling rig. It was designed, built, and launched in 1954. It was the first one in the world that was movable and reusable, and it drilled for 36 years here in the Gulf of Mexico.
Exploratory oil drilling deep under the sea is a complex task. A rig is positioned on the surface over a proposed oil well. Piping is extended to the seabed, through which a drill bit can descend and drill deep into the rock. If oil or gas are found, it can be brought to the surface through the riser pipe.
Our drill pipe is 30 feet long, threader in each end. It's hollow, and they pump the drilling mud, which is a clay that's ground up into powder. They pump it down there, and it brings the drilling returns back to the surface.
One of the most important elements in the entire process is the drilling mud. It helps lubricate the drill head, helps wash metal and rock out of the way. But most crucially, it acts as a physical barrier to prevent oil from rushing up the pipe.
From the seafloor, it comes up to the surface below the rotary table here on this white piece of pipe called a riser, so that it can go into the pipes that run into the beaches to the refineries.
To prevent explosions, it's crucial to stop oil and gas from rushing to the surface uncontrolled. So, in addition to using mud, engineers install a safety device called a blowout preventer, or BOP, that can close the wellhead at seabed level. This tried and tested method of deep-sea drilling has been practiced successfully for decades around the world, until 2010, when an incident in the Gulf of Mexico became worldwide headline news.
Deepwater Horizon was a mobile exploratory rig, basically a massive floating drilling machine that could tap into oil reserves in deep water far beneath the seabed. In fact, it had recently drilled the deepest well ever, at over 6 miles deep.
On April the 20th, 2010, Deepwater Horizon was drilling an exploratory oil well in an area of the Gulf of Mexico known as the Macondo Prospect. Investigative reporter David Hammer knows the story.
So there were 126 people on the Deepwater Horizon in April 2010. Most of them were from Transocean's drilling crew. They owned the rig, drilling it to try to get the riches out from about 5,000 feet below the surface of the Gulf of Mexico.
Having discovered oil, Deepwater Horizon successfully established a wellhead so that the oil could later be drilled and processed at the site. Suddenly, at around 8:45 a.m., the rig experienced what is referred to as a kick. A surge in pressure from a pocket of oil and gas.
Well, on April 20th, 2010, high-pressure gas came careening up this mile-long riser pipe from the well up to the rig, and oil was spewing all over the deck.
Within moments, the gas and oil rushing up the riser pipe found a source of ignition, causing an explosion. Deepwater Horizon was consumed by flames.
There were a series of massive explosions. 115 people were able to survive. There were harrowing stories about some of them actually having to jump 100 feet or more down from the deck and into the water, and then they had to be saved by life rafts. The captain of the vessel actually had to use a knife to cut loose from the side of the vessel in one of those life rafts to be able to go and pick up some of the survivors who had jumped into the water, and the water had burning flames on the surface. It was really a horrible scene.
Firefighters fought the blaze on the rig for 2 days before it finally sank.
As Deepwater sank, it ruptured the well pipe near the seabed. Tens of thousands of gallons of oil gushed uncontrollably into the ocean all day, every day for 3 months. It was the worst oil spill in US history.
Tragically, 17 workers were seriously injured and 11 people lost their lives. Now it was time for engineers to deconstruct what had gone wrong and determine how to plug the leak at the bottom of the ocean. As the Deepwater Horizon tragedy unfolded, the whole world looked on as oil and gas continued pouring into the ocean. The big question was what had gone wrong. Initially, there was little to go on.
The explosion scattered most of the evidence across the ocean floor.
Having discovered oil, Deepwater Horizon's team had poured a concrete plug into the well, a standard practice to contain the oil and gas.
The plug is the first line of defense against oil leaking into the environment, like a cork in a shaken bottle of champagne. If it's not sealed properly, the contents will fly out uncontrollably.
But creating this concrete plug deep under the ocean bed isn't straightforward. Structural engineer R.N. Silapan is a concrete specialist.
Right now, the concrete is pretty plastic, and as you can see, it's sort of in a flowable stage, and we want it flowing freely to go down the well hole and plug at the intended depth. But concrete in this state will not do the job. In order for it to plug effectively, it has to harden. We refer to it as curing. This is how a cured concrete would look. And in order to accelerate the curing process, they use nitrogen in that mix.
But in this case, deep beneath the ocean, with mud, seawater, and oil pressing in from all different directions, getting the mix and the plug just right was crucial.
The official investigation concluded that the concrete had failed to properly seal off the well, although it stated that it may never be able to identify the exact reason why. But investigators did discover another engineering fail that was present at the well head. The blowout preventer, or BOP, had malfunctioned. It contained a safety device called a blind shear ram that, in the event of an emergency, would automatically cut and seal the wellbore. Experts believe that the pressure of the blowout had caused the pipe inside the BOP to bend, preventing a clean seal. The oil pipe rupture created as Deepwater Horizon sank to the seabed was reported to have leaked nearly 5 million barrels of oil into the Gulf of Mexico. It took engineers 87 days to securely cap the broken pipe under the ocean. Lessons were learned by the oil industry worldwide, and there is hope that a catastrophe on this scale will never happen again.
This was one of those disasters that defined an industry, and a reminder for everyone of just how dangerous drilling for oil can be.
When innovating for industrial progress, engineers often take risks. When those gambles pay off, the benefits can be great, but if even one factor is overlooked, a disaster could be inevitable. Like this calamity at a Spanish dam.
This catastrophe was an ecological nightmare.
There was a real sense of dread.
An engineering oversight that threatened a national park.
It was a really toxic tragedy.
Andalusia, a region of southern Spain famed for its beautiful landscapes. And there is none more stunning than this UNESCO World Heritage Site, called Doñana.
This part, in particular, the Doñana National Park, is a renowned area of natural beauty.
Environmental journalist José María Montero Sandoval knows Doñana well.
Doñana es uno de los puntos calientes de la biodiversidad europea. Es una zona húmeda por la que transitan todos los años cientos de miles de aves en su viaje migratorio entre África y Europa. Por tanto, una zona valiosísima, tan valiosa que es patrimonio de la humanidad por la UNESCO, y además hay una notable comunidad científica que acude aquí todos los años a trabajar con toda la biodiversidad que hay en este territorio.
Andalusia is not only rich in natural beauty, it also has hidden riches underground. Lawrence Dollimore is a local journalist.
Andalusia is a very historic mining area where people have been mining for thousands of years.
This is the Los Frailes mine near the Doñana National Park. The mineral ore extracted from here contains valuable metals, including zinc, copper, lead, and silver.
The Los Frailes mine has been an important part of Spain's economy. It's provided jobs in the region, and the silver and zinc extracted here supplies the whole of Europe.
Mining in this area goes back thousands of years because it sits on what is known as the Iberian Pyrite Belt. It was formed by volcanic activity around 350 million years ago and is mineral rich. Geologist Dr. José Manuel Canto Romero explains.
En la faja pirítica tradicionalmente se ha aprovechado precisamente la pirita, que es el sulfuro de hierro, sobre todo en la época de la industrialización, como mena para el ácido sulfúrico. Pero en la actualidad, en el siglo XX, el aprovechamiento se ha hecho específicamente para cobre, plomo y zinc.
The mining process involves the extraction and separation of metal ores from underground.
Once the ore is out of the ground, a cocktail of chemicals is used to help extract the metals.
Sí, para obtener un aprovechamiento adecuado, con un rendimiento óptimo de esos metales, varían en función además de cada tipo de metal los rendimientos. Para obtener, por ejemplo, 1 kilo de cobre hay aproximadamente que tratar en torno a 100-140 kilos de mineral.
The extraction and refining of metal ores creates a range of byproducts in both liquid and solid forms.
The trouble is, the leftover sludge known as tailings is highly toxic. It can't be allowed back into the environment.
The solution at Los Frailes, as with many mines, was to create a dam in which the tailings could be buried.
A tailings dam is essentially a raised, man-made reservoir, surrounded by dam walls, in which the toxic byproducts from the mine can be safely contained.
The dam formed a lagoon above that contained water used in the mine. In effect, another byproduct of the process. This water was highly acidic.
All of these toxic materials were safely held within the dam until one day disaster struck. On April the 25th, 1998, at the Los Frailes tailings dam, one wall catastrophically crumbled to the ground.
Once the dam's integrity had been compromised, the pressure of the water held in the lagoon above was only going one way.
The land surrounding this section of the dam gave way.
The earth around the dam moved quite dramatically. One section of the dam was pushed 67 meters, that's almost 220 foot, in a lateral direction. This reduced the height of the dam crest significantly.
As the crest of the dam wall sank, it began overtopping.
Tons and tons of waste and toxic acidic water gushed down towards the town and the villages and the farmland. There was a real sense of dread.
The tailings from the Los Frailes mine contain traces of lead, copper, zinc, cadmium, and sulfides, and the water from the acidic lagoon. This toxic mix headed downstream into the Guadiamar and Agrio rivers.
As the toxic sludge continued to spread, the nearby Doñana National Park was now under threat.
Todo esto era, en aquellos días era un mar de lodo, ¿no? El río, el Guadiamar, se había desbordado por el agua contaminada y por los lodos, y todas estas riberas estaban cubiertas de lodos cargados de metales pesados, cargados de lodos tóxicos. Los árboles, por ejemplo, yo recuerdo que estaban cubiertos de lodo. Los pies de los árboles estaban cubiertos de lodo porque el lodo además se extendía muchos metros.
The scale of the catastrophe was shocking.
More than 2,000 birds were killed and tons of dead fish were found downstream.
Por tanto, el impacto en un primer momento era evidente, era muy fácil de ver y era fácil imaginar también qué impacto iba a tener en el futuro si no se hacía nada.
In the wake of the disaster, answers were demanded as to what had caused the dam to collapse.
Geotechnical experts suggest that the dam's foundation failed due to the chemical impact of toxins contained within the dam.
The foundations consisted of clay and calcium carbonate, which were exposed to a chemical attack from the acidic and pyritic slurries contained within the dam. With the foundations compromised, the pressure from the water within the dam caused a 20-meter section of the wall to collapse. Billions of liters of toxic slurry were released.
El agua que hay detrás en la balsa pues es la que ha empujado toda la pirita flotada que ha avanzado, desgraciadamente, hacia el Parque Natural de Doñana. Pero puede decirse que la causa de la rotura es simplemente una superación de la capacidad portante del terreno, en este caso de esas margas azules, y ese fue el gran fallo técnico que aquí se produjo.
When the dam breached, engineers had to act quickly to minimize the threat to the local ecosystem.
With toxic sludge and acidic water on the move, the race was on to stop it in its tracks. A temporary dam was quickly constructed downstream. It prevented the national park from being completely decimated, but a great deal of damage had already been done.
Now it was up to emergency workers to clean up the toxic waste and save Doñana.
La obra de restauración del Guadiamar fue una obra faraónica, que se hizo en gran medida gracias a la presión de la comunidad científica, ¿no? Hay que imaginarse que en pocos meses, en poco menos de un año, se retiraron 7 millones de metros cúbicos de tierra contaminada, 500 camiones operando prácticamente las 24 horas del día, recorrieron 17 millones de kilómetros y fueron muchas personas trabajando constantemente en todo lo que era el río, en todo lo que eran las márgenes del río.
The cleanup operation was huge. Over 4 million tons of this toxic sludge had to be removed, along with 400 million cubic meters, so that's 106 billion gallons of acidic water. All of this had the hefty price tag of $100 million.
Worryingly, some experts have speculated that it could take up to 40 years for the affected farmland and wetlands to fully recover.
Following the incident, the Los Frailes mine was closed for 17 years. To resume mining, engineers had to come up with new, safer ways of dealing with tailings.
Lessons were learned so that hopefully this type of disaster will never happen again.